Hi everyone, this is Professor M. Science, and today I want to talk about the degeneracies of the isotropic three-dimensional quantum harmonic oscillator in another one of our videos on rigorous quantum mechanics. The three-dimensional quantum harmonic oscillator is a simple generalization of its one-dimensional counterpart. The energy eigenvalues are simply obtained by adding up the eigenvalues of the one-dimensional oscillators along the Cartesian directions, and the energy eigenstates are obtained by simply taking the tensor products between the energy eigenstates of the one-dimensional oscillators along the Cartesian directions. Despite this apparent simplicity, today we're going to study a really interesting feature that emerges when this quantum harmonic oscillator is isotropic, which means that it looks exactly the same in all directions. For an isotropic oscillator, the energy levels become highly degenerate. And this means that there are many different states that share the same energy. Today we're going to explore how this arises mathematically, and we're also going to visualize what these energy eigenstates look like. So let's go! Today we consider a particle moving in an isotropic three-dimensional quantum harmonic oscillator. The discussion builds on the general three-dimensional quantum harmonic oscillator, so if you haven't seen that video yet, I recommend that you check it out before you continue with this one. As a very quick reminder, the Hamiltonian H of a three-dimensional quantum harmonic oscillator is given by the kinetic energy of the particle moving along the x direction, plus the kinetic energy of the particle moving along the y direction, plus the kinetic energy of the particle moving along the z direction. And we also need the potential energy terms, the one along the x direction, along the y direction, and along the z direction. This expression has the full explicit Hamiltonian in the tensor product state space used to describe the motion of particles in three spatial dimensions. However, we know that when we work with tensor product state spaces, we tend to simplify our notation by omitting the various identity operators and tensor product symbols, and in this simpler notation, the Hamiltonian H is given by the three kinetic energy terms and the three potential energy terms. Okay, that was a quick intro, but hopefully you should all be familiar with all of this already. Today, we're going to consider a special case of this Hamiltonian, the isotropic case. What this means is that we will choose the frequencies along the different directions to be equal to each other, and we will collectively call them omega. Using the simplified notation, we can very quickly rewrite the Hamiltonian with the same kinetic energy terms and with the new isotropic potential energy terms. And we can actually take common factors to simplify the kinetic energy terms, and we can also take common factors to simplify the potential energy terms. Feel free to pause here for a moment to convince yourself of these expressions, but everything should be pretty straightforward. Now, we've already solved the general three-dimensional quantum harmonic oscillator up here in the corresponding video, and the solutions to the isotropic case can be simply taken as special cases of the general solution. So it may sound a little silly that we should have a full video looking at this specific problem. However, what we will see today is that in the isotropic oscillator, we have a particularly nice feature that doesn't occur in the general case. We have plenty of degeneracies in the energy spectrum. Now, before we properly launch into the isotropic case, let's briefly recall the general eigenvalue equation of the three-dimensional quantum harmonic oscillator. Using the simplified notation for the Hamiltonian, we can regroup the x-dependent terms, the y-dependent terms, and the z-dependent terms. This here is a Hamiltonian of a one-dimensional quantum harmonic oscillator along x. This is also a one-dimensional oscillator, but now along y, and this is also a one-dimensional oscillator along z. So that the Hamiltonian for a particle in three dimensions is simply the sum of the Hamiltonians of the particle moving along the three Cartesian directions independently. We can write the eigenvalue equation for a one-dimensional quantum harmonic oscillator in the usual way, where these are the eigenvalues and these are the eigenstates. And we have one such equation for every Cartesian direction x, y, and z. And you will also remember that the eigenvalues are quantized and given by this expression where the labels n alpha are non-negative integers. The eigenvalue equation for the three-dimensional oscillator is given by h, acting on the eigenstates, which are given by the tensor product of the eigenstates of the one-dimensional oscillators, equal to the energy eigenvalues times the eigenstates. From the video on the general three-dimensional quantum harmonic oscillator, we know that the energy eigenvalues of the three-dimensional quantum harmonic oscillator are given by the sum of the energy eigenvalues of a one-dimensional harmonic oscillator along the x direction, that of a one-dimensional oscillator along the y direction, and the equivalent term along the z direction. And we can also spell these out explicitly as the term along x, the term along y, and the term along z. If we now move to the isotropic oscillator, we have that omega x is equal to omega y, which is also equal to omega z, and all are equal to omega. And this means that when we write the energy, we can take h bar omega as a common factor, and then this multiplies nx plus ny plus nz plus 3/2. We see that for an isotropic oscillator, the energy does not depend on the individual nx, ny, and nz, but only on this sum. And we can define this sum to be n. Now this implies that we don't need to label the eigenvalues with all three indices nx, ny, and z, but instead we can simply label the eigenvalues with the single index en, and they are equal to h bar omega times n plus 3/2. The new collective index n is given by the sum of the original indices, and remembering that the individual nx, ny, and nz are non-negative integers, then this means that n must also be a non-negative integer. So what does this mean? There are multiple combinations of values of nx, ny, and nz that add up to the same n, and therefore give the same energy. This means that the energy eigenstates of the isotropic three-dimensional quantum harmonic oscillator will in general have some degree of degeneracy. And the aim of this video is to explore this degeneracy, and we will seek to calculate Gn, the number of different states, with the same energy En. But before we launch into the degeneracy, let's briefly look at the eigenfunctions of the system, which will also prove necessary for our discussion. From the video on the general three-dimensional quantum harmonic oscillator, we know that the eigenfunctions psi nx, ny, nz of x, y, z are simply given by the product of the eigenfunction of a 1D harmonic oscillator along x, a 1D harmonic oscillator along y, and a 1D harmonic oscillator along z. As a reminder, the eigenfunction of a 1D harmonic oscillator is equal to a prefactor multiplied by a Hermite polynomial multiplied by a Gaussian exponential, and this is true along the x, y, and z directions. In these expressions, I've already assumed that we're working with an isotropic oscillator, so the frequency does not depend on the direction alpha here, here, or here. However, unlike the energies, which only depend on the sum of nx, ny, and nz, the eigenfunctions do separately depend on the index n alpha. And this is the key observation. We're going to find that for every degenerate energy level, we have a family of distinct eigenfunctions with the same energy. We're now ready to study degeneracies in the energy spectrum of the isotropic oscillator. And the strategy that we will follow will be to first consider a few examples, and then we will finish with the general result. So let's start with the ground state n equals 0. The ground state energy E0 is equal to 3/2 h bar omega. How many distinct states have this energy? To answer this question, we need to consider how many triplets of non-negative integers nx, ny, and nz add up to 0. And there's clearly only one possibility. All of them must be equal to 0. What does this mean? This means that the ground state is non-degenerate, so that the degeneracy of the ground state, G0, is equal to 1. We can easily construct the corresponding wave function, which is simply given by the product of the ground state wave functions along x, along y, and along z. Remembering that the ground state wave function of the one-dimensional quantum harmonic oscillator is simply a Gaussian, we can write this full wave function as equal to this combined prefactor times this Gaussian. We see that this wave function only depends on the distance from the origin, so it is spherically symmetric. Now, it is impossible to plot the eigenfunctions of the three-dimensional oscillator, as we would need a four-dimensional space to do so. However, we can visualize them along the different spatial axes where they essentially look like their one-dimensional counterparts, and so this is what we're going to do. This diagram here shows three slices of the full ground state wave function of the isotropic three-dimensional quantum harmonic oscillator. The top panel shows the slice along the x-axis, the middle panel is the slice along the y-axis, and the bottom panel corresponds to the z-axis. We see that we have the ground state for each of the three one-dimensional oscillators making up the full three-dimensional oscillator. Each contributes the corresponding 0-point energy of 1/2 h bar omega, and the three add up to the full 0-point energy of 3/2 h bar omega of the three-dimensional isotropic oscillator. Let's next consider the first excited state with n equals 1. The energy E1 is equal to 5/2 h bar omega. So, how many distinct states are such that nx plus ny plus nz equals 1? There are three possible choices for nx, ny, and nz. The first is 1, 0, 0, and the corresponding wave function has the first excited state for the one-dimensional oscillator along x, and the ground state for the other two. The second choice is 0, 1, 0, and the corresponding wave function has the ground state along x, the first excited state along y, and the ground state again along z. And the third choice is 0, 0, 1, and the corresponding wave function is given by the ground state along x and along y, and the first excited state along z. These three wave functions are different because the first one has the excited state along x, the second one along y, and the third one along z. However, they all lead to the same energy E1 up here. And this means that the first excited state of the isotropic three-dimensional quantum harmonic oscillator is triply degenerate, so that G1 is equal to 3. Unlike the simple mathematical form of the ground state wave function, the wave functions of the excited states have longer, less intuitive expressions, so rather than writing down their explicit mathematical form, we will directly visualize them. Let's visualize the triply degenerate first excited state. These diagrams again show slices of the full first excited state wave function. This particular example corresponds to the case where the extra quantum of energy is added along the x direction, so that the total energy contribution from this direction is 3/2 h bar omega, while the system is in the ground state along the y, contributing 1/2 h bar omega, and along the z direction, also contributing 1/2 h bar omega. Their combined contribution adds up to 5/2 h bar omega, the total energy of the first excited state of the three-dimensional quantum harmonic oscillator. This second example shows a distinct first excited state in which the excitation is along the y direction, contributing 3/2 h bar omega, the x direction contributes the 0-point energy, and the z direction also contributes the 0-point energy. Despite a different distribution of the overall energy, their combined distribution again adds up to 5/2 h bar omega. And you can now see how this will work in the third distinct first excited state. The additional energy quantum in this case is along the z direction in the bottom panel. Right, so putting everything together, what these diagrams show is that to get to the first excited state of the three-dimensional isotropic oscillator, we essentially need to add one quantum of energy to one of the individual harmonic oscillators along one of the spatial dimensions. It doesn't really matter which one we excite, because the oscillator is isotropic, so excitations along any direction will provide the same energy. We have three different possibilities with the extra quantum of energy along the x, the y, or the z directions. And these three possibilities give a triply degenerate first excited state. Let's now consider the second excited state with n equals 2. The energy E2 is equal to 7/2 h bar omega. So how many distinct states are such that nx plus ny plus nz equals 2? There are 6 possibilities now for this triplet. The first 3 distinct states are simple extensions of what we already discussed for the first excited state. They are 2, 0, 0, with this associated wave function, which is given by this product. Then we have 0, 2, 0, and the corresponding wave function given by this product. And we also have 0, 0, 2 with the corresponding wave function given by this other product. Now this situation is essentially equivalent to the one that we had for the first excited state, in the sense that the excitation is along one direction only, and it can be along x, y, or z. And the only difference is that we're now adding 2 quanta of energy. But we have another 3 possibilities, because we can also have the 2 extra quanta of energy spread across different directions. We can have 1, 1, 0 with this associated wave function given by this product, 1, 0, 1 with this associated wave function given by this product, and 0, 1, 1 with this associated wave function and given by this other product. This situation is qualitatively different, as now there is an excitation along 2 different directions, in the first case along x and y, in the second along x and z, and in the third along y and z. All of these lead to the same energy E2 up here. And this means that the second excited state of the isotropic 3-dimensional quantum harmonic oscillator is 6-fold degenerate, so that G2 is equal to 6. Let's visualize the 6-fold degenerate second excited state with the usual diagrams. The first column corresponds to the case where the system reaches the second excited state by adding 2 quanta of energy along the x direction. The second column shows the distinct excited state in which the 2 quanta of energy are added along the y direction, and the third column is the same thing but for the z direction. As we've discussed, these 3 cases are a simple extension of what we had in the first excited state, with the 2 extra quanta of energy being added along one of the 3 spatial dimensions, and it doesn't really matter which one it is, because the system is isotropic. But we now have 3 more possibilities. The fourth column shows the case when we add 1 extra quantum of energy along x and 1 extra quantum along y. The fifth column adds 1 quantum along x and 1 along z. And the sixth column adds 1 quantum along y and 1 along z. In this second group of 3 states, the 2 quanta that we need to add to the system are shared between 2 spatial dimensions. So why do we have so many possibilities? This is actually not a general result for any 3-dimensional system. It is a special feature of the quantum harmonic oscillator. The key is that the energy eigenvalues of the quantum harmonic oscillator are equally spaced. The energy quantum is always h bar omega between any 2 levels. This means that we can add the exact same energy by adding 2 quanta along some particular direction, like we do in the first 3 cases, or by adding two quanta along two different directions, as we do in these other three cases. So let's finish by generalizing these results. What is the degeneracy of a general energy eigenvalue En? We need to figure out how many triplets nx, ny, and nz are such that their sum is equal to n. To figure it out, let's first fix nx. Then ny plus nz must be equal to n minus nx. How many choices do we have for ny and nz? The first is that ny is 0 and then nz must be n minus nx. The second is that ny is 1 and then nz must be n minus nx minus 1, and so on, all the way to ny being n minus nx and nz being 0. If we consider all of these possibilities, we get a total of n minus nx plus 1 terms. This means that the degeneracy Gn of state n is given by the sum over all possible choices of nx, and we've just figured out that for every such choice we have n minus nx plus 1 terms as possible choices of ny and nz. N and 1 can be taken out of the sum, so we end up with this term minus the sum over nx. This is just n plus 1, and this is a standard arithmetic series which is equal to this. Putting everything together, we end up with 1/2 times n plus 1 times n plus 2. And this is our big result. The energy eigenvalue En of the isotropic three-dimensional quantum harmonic oscillator has degeneracy 1/2 times n plus 1 times n plus 2. You should convince yourself that this general result is really consistent with the three examples that we've discussed. But more generally, we see that the higher the energy level, the larger the degeneracy. This again arises from the fact that the energy levels in a harmonic oscillator are equally spaced, and that in the isotropic oscillator, the spacing is the same in all three spatial dimensions. Now, conceptually, the higher the energy, the more ways we can distribute it amongst the three directions. I want to finish with two brief points. First, there are some very interesting underlying symmetries that lead to degeneracies of the isotropic quantum harmonic oscillator that we've explored today, and we may get into that in a future video. Second, as the energy eigenvalues are degenerate, this means that the corresponding eigenstates are not uniquely defined. It is actually interesting to explore alternative choices for the energy eigenstates, and we describe a different approach to the isotropic three-dimensional harmonic oscillator in the context of central potentials, so I encourage you to check out those videos. The isotropic three-dimensional quantum harmonic oscillator has a highly degenerate energy spectrum. Among other things, what this means is that there isn't a unique choice for the energy eigenstates in any given degenerate subspace. In fact, in our videos, we find isotropic harmonic oscillators in a different context as well, when we study central potentials. I therefore really encourage you to check out those videos as well, because there we write down the energy eigenstates in a completely different way. And as always, if you liked the video, please subscribe.